Welcome to NASA Edge.
An inside and outside look at all things NASA.
Well, I got to say, you probably couldn't see the rocket because of all the fog, but there is a rocket behind there.
That's right. There we do have a little bit of weather rolling in. Not the best aesthetic shot,
Right.
but certainly doesn't matter. It's not a bad condition for launch, so everything's still all systems go here.
Hey, we got a great show today. We're going to be talking all things Jason 3 as we get set for the launch in less than an hour. And outside right now is Franklin. I think he has a pretty good spot, but he probably sees a lot of fog too. Franklin, how are things going out there?
Oh, guys, it's actually a little chilly out here. The conditions are overcast. The weather's been kind of on and off here in Vandenberg since we arrived a couple of days ago. Over my shoulder, or beyond this hill, a couple miles going toward the coast, is Slick 4. And that is where Jason 3 rests right now. Not sure if we're going to be able to see it if this fog stays where it is, but from what I understand, these conditions aren't the type of conditions that can actually keep the rocket from lifting off. So we'll see.
Hey, thanks a lot, Franklin. And joining us now is John Grunsfeld, who's the Associate Administrator for the Science Mission Directorate at NASA headquarters. How you doing, John?
I'm doing great.
Hey, it's been only about a few months ago since we caught up with you in Fort Sumner, New Mexico on another cool mission called RADx.
Yep, RADx was really a great mission, and also interested in the interaction between the sun, the radiation environment from the sun, the atmosphere, and the Earth. Today we're focusing on the Earth.
Absolutely, and in fact, Jason 3 is the focus today. And before we get into the specifics of Jason 3 later in the show, I kind of want to focus on the broad picture of Earth science. We have a campaign at NASA, it's Earth Right Now, because Earth is very important to us. From a NASA perspective, what are we doing to sort of learn more about the Earth and to analyze the Earth and kind of understand climate change?
Well, as you know, I've spent most of my life trying to get off of planet Earth. And one of the amazing things about looking back at planet Earth from space is that you can see its complexity. You can see the interaction of the oceans with the atmosphere. You can see ocean currents. And it's a thorny problem to try and understand the heat transport from the equator up to the poles, to try and understand how the oceans and the atmosphere interact to create the weather we see. And of course, some of that weather is really important. For instance, the development of hurricanes. And it's that coupling between the ocean and the atmosphere that generates the power in hurricanes. And so what NASA is trying to do with our Earth Right Now, with our Earth science, is understand the Earth as a system, all the coupled components. How does the ocean and atmosphere interact? How do the ice caps at the poles, Greenland ice cap, how do they contribute to sea level rise and the dynamics? How does the solid Earth work? It's all of those pieces working together that will give us the kind of knowledge we need to predict what's going to happen in the future. And also, it's just really interesting. We study planetary science at NASA. Well, the Earth is a planet,
right,
and the one that in some ways is both the easiest to study, because we're here,
right,
and the hardest to study, because we get to see it in all its glorious complexity.
Right. And of course, for a lot of people out there, the weather here today in Vandenberg, it's probably a result of weather halfway around the world at some point a few days ago. It's all interconnected.
It is all interconnected. In fact, the weather here in Vandenberg and in California is being significantly affected, as many people know, by the El Nino,
right,
which is this big slug of hot water, warm water, that's made its way east.
Right.
And has changed the weather in California significantly from last year and really the last decade. And it's exactly that kind of process that the Jason 3 mission that we're going to launch in just a few minutes is going to help study.
We're here at NOAA's Center for Weather and Climate Prediction with Jim Silva, the program manager for Jason 3. Jim, tell us, what is Jason 3?
Well, Jason 3 is not the third in the series of the Halloween horror flicks that we keep seeing. It's actually a
bummer.
It's actually a very important scientific satellite that will help the operational oceanography community, the Weather Service, the U.S. Navy, for instance, and the Coast Guard to provide for safe navigation and safe maritime observations. This satellite provides significant wave heights, sea surface heights, and wind velocity. So with those three products, we can deliver many other products that'll help the Weather Service, our colleagues in Europe, the climate community, which is very much interested in assessing the rate of sea level rise, and the National Hurricane Center to determine whether a hurricane will intensify as it approaches a warm spot in the ocean.
It's interesting. You said sea surface height. How do you determine sea surface height from space?
Well, this satellite has a very precise instrument called an altimeter that measures the time that it takes for a signal to return back to the radar. And with 4 other instruments on the satellite, we're able to adjust the measurements so that we can get a very precise measurement of the distance between the satellite and that sea surface height.
Yeah, now it's interesting because you mentioned partners. You mentioned some folks in Europe, and then of course you're working with NASA. So
Yes.
Explain these partners.
Well, we really get a terrific return on our investment at NOAA, and it's because we have our European partners contributing practically half of the entire mission cost for Jason 3. The French Space Agency, CNES, provides the satellite and 2 instruments on the satellite. Our colleagues at EUMETSAT in Germany, they provide for a ground system station. On the US side, through NASA, NOAA provides the launch vehicle, the launch services, 3 of the instruments on Jason 3. We also will be processing, distributing, and archiving the data. And through the help of the science community, we improve the products that we generate by the algorithms that we integrate into our processing systems.
How do you go about making the data available to all the partners and then to others that might benefit down the road with the data?
Okay, so what we do at NOAA is once we process the data, we send it to a server that will then make it available to our partners, to NASA, and to other users who request the data. There are 2 types of data: the operational geophysical data records, which are basically near real-time products that are delivered within 3 hours from observation, and the offline products that take some time to generate. And those are the more accurate climate sea surface height measurements that are used and are in demand by the climate community.
I'm sure you get this question a lot. What is the difference between Jason 2 and Jason 3?
Yeah, that's my favorite question because the answer is almost nothing. Actually, the Jason 3 mission is built to be almost identical to Jason 2. And that's good for us because we're climate scientists. You know, one of the things that Jason measures is global sea level rise. That's incredibly important. And we want to make sure we're seeing changes in the ocean and not changes from one satellite to the next. So we're comparing apples to apples.
So it's almost a carbon copy except for a few new additions.
Right. One of the things actually is not really an addition, but it's something new we're going to do with it. Every once in a while, we'll tilt the satellite back and look out into space with one instrument called the radiometer. That's what helps us correct for the amount of water that's in the atmosphere. The way the satellite basically works is it bounces a radar wave off the ocean and measures the return time. But if there's more water in the atmosphere, it takes a little longer. So this radiometer measures that, and every once in a while we'll tilt back and look off into deep space, and that'll help us calibrate it so we keep the integrity of our long-term record just a little bit more accurate.
Well, not only the radiometer, but the GPS was also built by NASA.
That's right. So the GPS is important because it tells us where the satellite is. We want to know the height of the ocean, so that means we need to measure the distance between the satellite and the water, and also we need to know where it is. So those 2 pieces of information tell us the height of the ocean. And then JPL also purchased and supplied a laser reflector, so it's just a little set of mirrors that bounce a laser back. That too helps us locate the satellite in space so we know its position very accurately.
Lori, we kind of understand what Jason 3 is going to do, but why do we need the science that we're going to get from Jason 3?
Well, Jason 3 is designed to measure sea level all over the globe and do it in a way with great precision and accuracy, from which we can determine a whole host of issues that NOAA needs for its operational forecasting purposes. On the smallest timescales, talking about something that might be of interest to forecasters dealing in hours or so, what we're able to do is we're able to actually measure the wave characteristics as waves are coming into shore and the waves offshore, which the mariners need. On a slightly longer time scale, like hours to days, NOAA uses the data coming from JASON for hurricane forecasting. Now, it may sound complicated to you.
It does.
Measuring sea level from space turns out to be an important thing for hurricanes because hurricanes feed off the heat energy that is stored in the upper layers of the ocean. And that heat energy causes the ocean to expand and create a bump in the surface of the ocean. And the altimeter on JASON 3 can actually see those bumps. So for example, if we know that a hurricane is going towards one of these areas where there's a large pool of warm water, something that we can see in JASON 3, then what we can do is we can build that information into our models and actually forecast the increase in the strength of the hurricanes. For example, the recent Hurricane Patricia that landed in Mexico, that cranked up from about a 2 to a 5 category hurricane, in part because it went over a patch of warm water that the altimeter could see. Now, I've been talking about the kind of forecasting that most people are used to. Sure. There's another kind of forecasting that we're all really interested in, and that is what happens over long periods of time. And the JASON series is actually the primary tool for us for measuring global sea level rise and regional and local sea level rise. Something that is capturing a lot of attention today because people understand the climate is warming, it's largely due to a human activity, and we have to understand how these changes are occurring so we can prepare for them.
It's interesting to me because this seems like to get the picture that you need, you can't just do this with one, you've got to do it with more satellites and over time.
Well, you need a long record because the changes that we're seeing, what I'll call the climate changes, are something that are evolving over many tens of years. An example, sea level rise is now rising at a rate that we believe is twice as fast as during the last century. But we can tell that because we've made measurements over many years. In the JASON series, more than 20 years.
So are you planning JASON 4, 5, and 6 down the line? Because obviously the bigger...
Absolutely. This is, for all practical purposes, a series of satellites that will continue. And it will continue largely because we anticipate, and the models project, sea level is going to probably rise over the next 100 years at least 3 or more feet, with tremendous impact in our coastal areas.
With the launch of JASON 3, though, you will extend that time frame. But how about the previous JASON satellites? Are they all going to operate concurrently, or how does that work?
And in fact, satellites generally don't last forever. We know that. So what we're doing is we're launching successive series of satellites. And what we're doing is we're doing it in a way so that we ensure a time overlap from one satellite to the next. So for example, when we launched JASON 3, JASON 2 is still operating, but it's nearing the end of its expected lifetime. And so we put the two satellites up close together and we fly them for a certain period of time to get a direct intercomparison. Mind you, we're trying to make incredibly precise measurements, and to do that we need to intercompare the satellites.
And of course, that continues all 3 phases that you mentioned. You've got your ability to give short-term prediction, the hurricane forecast, but then also the big range
Absolutely,
data as well.
That's a critical aspect of this program. Another example, I skipped over one of the timescales that...
Bonus data.
Bonus data, yeah. For example, we're now in the middle of a big ENSO, El Nino Southern Oscillation. It's something that the public is rapidly becoming familiar with because we're now seeing excessive rainfall in the southeast and in California and droughts elsewhere. All of that is a feature that in large measure occurs in the Pacific Ocean. And in fact, the altimeter on JASON 2, JASON 3 can observe the progression of the development of El Nino. And it's actually in part from the measurements from the altimeters that we can actually predict the evolution, how over time an El Nino will develop. So we have some notice in advance and people can make preparations.
We are very pleased to have special guest with us, Jean-Yves Le Gall, who's the president of CANES. Thanks so much for coming on the show.
Thank you.
Well, listen, we're really excited. Jason 3 is obviously a very, very important mission. One of the things that we're wondering is, how does Jason 3 figure in to CNES's overall mission?
No, Jason 3 is very, very important because, as you know, climate and monitoring of climate change is one of the essential missions of CNES. And as you know, a few weeks ago, we hosted in Paris the COP21 conference on the climate, which is a huge success because of the very close cooperation between President Obama and President Hollande. And Jason 3 will be an element of this study of climate, and we are very excited of this launch today.
Now, you talked about some of the partners and working with NASA, working with NOAA. How important is it for you as president of CNES to develop and foster those relationships moving forward?
I think that space is global, and so what we are doing must be global. And this is why we have many cooperations worldwide, but with the US it's very specific because with NASA we are on Mars on Curiosity. With JPL we have a long-standing cooperation in oceanography, and we are going to continue because after Jason 3, Jason CS is already on tracks, and we are working on many other very exciting projects, and so it's very, very important for us.
Now, I understand that Jason 3, the spacecraft, was actually built by a company in France. Were you able to visit the facility and check out?
Yes, of course. Jason 3 has been developed by CNES in close cooperation with Thales Alenia Space, and I saw it in the factory. It's always with a lot of emotion when you see the birth of a spacecraft. At the beginning, you have the basic components, then the optics, then the frame, then the solar array, and step by step you see the spacecraft which is built, and now we are in the final step because if everything is going well, in a few minutes we will have it in orbit.
Now, I understand in your background you have an engineering background?
Yes, I do.
So when you went to the company to check on this process, were you tempted to get in there and start working on it yourself?
You see, I was an engineer, but a long time ago, and I have too much respect for engineers to do anything. I just look at what people are doing, nothing else.
Well, sure. It's just very cool to think that you were actually able to see it. We saw it arrive and as it was being processed here, and totally understand that emotion, because it is really something to see everything finally come together right before a launch.
Yes.
And of course, with Jason 3, the spacecraft was built in France, and then it came over to the United States on board a 747, and we actually have some video of the vehicle coming over. So kind of take us through the process here.
Sure, this is the 747 landing at Vandenberg Air Force Base, and this is view. They're getting ready to offload the spacecraft itself. That's in a large container that's environmentally controlled. Here it comes down the scissor lift, and they're going to put it on a flatbed truck and haul it out to the payload processing facility that is right near the pad down at Space Launch Complex 4. Here they are approaching the gate to Space Launch Complex 4. So here's the truck near the PPF, taking the tarp off and getting ready to open the doors and move that into the payload processing facility. And like I mentioned earlier, this was the first time it was used, and here they're rolling right through the integration facility where they process the boosters. You see a booster there on the right-hand side. They're rolling it to the back, and in the back there is a door that will take you right into the PPF. Here we go, taking the lid off of the transport container. You can finally see the spacecraft with some bagging material around it.
Now, it's not a very big spacecraft in terms of other ones we've seen here in the past.
No, it isn't very big, but it was an economical choice to use the SpaceX booster.
Very good.
And here we're rotating the spacecraft to vertical, and of course now when you hook up the electrical test kits and do your testing and prepare the spacecraft for fueling.
Right. Bolts are important, right?
Bolts are important. Make sure you put those bolts in. That's right. Exactly. So this is just a video survey of some activities. There's a man looking at a witness plate that is there to collect any kind of particulate to give you an idea if the spacecraft is seeing any kind of contamination. And that's just a nice shot of the spacecraft, probably before they're going to fuel it.
And as you said, this is the first time using this facility here.
Absolutely.
Okay.
And as I mentioned, we were quite happy. There in the foreground, you see the payload adapter fitting.
Right.
They're going to lift the spacecraft to that fitting, and then eventually it will fit to another larger fitting that will mate to the booster.
Yeah, we were talking earlier this week, when they put the spacecraft to this adapter and then add it to a bigger adapter, it kind of looked like the Orion spacecraft.
Yeah, it kind of does, but I just want to assure everyone there's nobody inside.
Oh, okay, very good. That's good to know. And then, of course, once it's mated to the spacecraft adapter, eventually it will be mated to the launch vehicle itself. Now, as being a part of the Launch Services Program Office, how do you determine which launch vehicle to use for a particular mission?
Well, that's a good question. So it depends on the performance, where the spacecraft needs to be in orbit, the size of the spacecraft. Those kinds of factors weigh in on what type of launch vehicle can meet that need. And then, of course, there's always cost.
And then also, too, we get a lot of questions from viewers all the time. Is what's the difference between launching from Vandenberg, which is on the west coast of the United States, as opposed to, let's say, Cape Canaveral?
Well, the biggest difference is the rotation of the Earth, and you get help on the East Coast from a performance perspective, energy perspective, launching from the East Coast that you don't get here on the West Coast. And of course, the West Coast launches go into a polar orbit rather than equatorial.
Okay, so it just depends on where the spacecraft is going to be orbiting.
Needs of the mission drive which site you would launch from.
Now let's go ahead and take a look at the pad, because John, I think we still have the fog. Oh, we see the rocket. We actually see the rocket now, but it was before we didn't see it. So.
You bet. So the weatherman said we'd have about 3 miles of visibility with the fog, but so hopefully we'll see something.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of the Falcon 9 rocket with Jason 3. Continuing the mission for global insight into ocean sea surface height and its effects on our planet.
First stage propulsion nominal. Vehicle pitching downrange. First stage PU is active. Copy that.
As of right now, we know that spacecraft is in coasting phase. Everything's looking pretty good.
Yes.
And so, but unfortunately, that wraps up our coverage. For the live show for Jason 3. It was fun.
It was a great launch, very successful. It's just interesting. Our first daytime launch and zero visibility from the ground. And we heard it. It was very impressive from an audio standpoint. You could actually feel it.
Oh, you felt it. Oh,
but
definitely.
We were all looking around. In fact, I thought maybe I was looking in the wrong direction a couple of times. But it's just good to see that this finally come off. And after talking to everybody, all the partners, they're clearly very excited, and as we all are. And to see this launch be successful is a great thing. I'm happy for everyone involved.
Thank you again for watching our Jason 3 live coverage. You're watching NASA Edge.
An inside and outside look
at all things NASA.